All right, so yesterday we started out talking about electrophilic aromatic substitution, and we said that we really can't do addition reactions with aromatic molecules because we'll break aromaticity. But the weird observation was this substitution reaction works as long as you have iron present. And so we went in and we talked about how iron will actually coordinate with elemental bromine to make this super duper strong electrophile. The key takeaway from all of these reactions is they only work if you have a really, really, really strong electrophile. Why is that? Because our nucleophile is super weak, right? So if our nucleophile is super weak, the only way we can counteract that is to have a much, much stronger electrophile to push these reactions. All right, so the reaction we're going to start with today is nitration. It's along the similar lines as what we've seen before, and again, we need to come up with a super duper strong electrophile. So first, let's look at the overall reaction. The overall reaction involves any sort of aromatic molecule. It doesn't have to just be benzene. It could be a substituted aromatic molecule, or it could even be a heteroaromatic molecule. And then in this reaction, we're going to treat this with nitric acid, which is HNO3, along with sulfuric acid. When you do this, you can add in a nitro group. And nitro groups are pretty unique. They have Zwitter-ionic character. However, it's important to remember that this negative charge doesn't reside on one oxygen. It's actually being shared between both oxygens. So really the formal charge of each oxygen would be what? -0.5 or -0.5, right? So in this case, it's important to remember it does have Zwitter-ionic character, but it's not localized. All right, so the reactivity is pretty neat, but I did want to show one example of this in action. What's this molecule called? Toluene. All right, and if you treat toluene with excess nitric acid and sulfuric acid, you're going to be in for a fun time, or maybe not so fun time, depending on who you ask. You can actually add in multiple nitro groups. And what is this called again? TNT. So sometimes you do have to be careful when you're nitrating because the more nitro groups you add onto aromatic molecules, the more explosive they tend to get. However, it's hard to over-nitrate a molecule, and we'll talk about why that's the case later. So normally you don't have to run into this problem of accidentally making an explosive. Oh my goodness. All right, so let's take a look at the mechanism. All right, the mechanism starts out with our nitric acid. And nitric acid is kind of unique as an acid. It also has Zwitter-ionic character. Again, the negative charge on that oxygen can be delocalized across both the oxygens. So really it's a -1/2 charge for both of those oxygens. And it's monoprotic, right? And then we also have sulfuric acid floating around in solution. My question for you is, which is the stronger acid, nitric acid or sulfuric acid? Why is sulfuric acid going to be more stable as a conjugate base? Has more resonance, has minimized charge. Yeah, so sulfuric acid is definitely a much stronger acid, which means it's going to actually protonate nitric acid. It's weird to think of nitric acid acting as a base, but in this case, it's being outcompeted by sulfuric acid because sulfuric acid is so strong. Okay, so in this reaction, one of these oxygens, or I should say that oxygen, steals a proton from the sulfuric acid because sulfuric acid's a really strong base. or sorry, sulfuric acid's a really strong acid, therefore nitric acid's going to act as a base. Excuse me. And now we end up with this highly charged intermediate. Yep.
Is it attacking that oxygen, not the other one, just as the residence between the two oxygens? Like, why not?
So your question is, why isn't this oxygen acting as the nucleophile? The reality is it could. However, it wouldn't take us in any sort of meaningful direction. We'll take a look at why this is a useful direction here in a second. One thing I notice is we talked a lot in term 1 and term 2 about leaving groups. And in this process, we've generated a good leaving group. Right? If we had protonated the other oxygen with a negative charge, we wouldn't have made that into a good leaving group, right? But by doing this oxygen, by protonating the oxygen on the right-hand side, we've created a relatively good leaving group. All right? That means it can be shoved off. So this oxygen can clamp down and eject off water as a leaving group. And then we get this ion that is really, really reactive. This ion is called the nitrosonium ion. And it's a very strong electrophile. All right, the byproduct in this reaction is going to be water along with your conjugate base of sulfuric acid. However, normally your sulfuric acid is just almost acting like a solvent in this case, so it's floating around in excess. So we've created this nitrosonium ion that's a really, really good electrophile. We can have this react with any sort of aromatic molecule. It can be substituted, it can be heteroaromatic. In this case, I'm just using benzene because it's easy. And it's going to act as a nucleophile that will attack this newly generated electrophile. So we can show this attacking in, kick up electrons onto the oxygen, and then we're going to make that sigma complex that we've seen a few times before. All right, so we've got this sigma complex. We've got a positive charge over here. What do you think the next step's going to be? Yeah, we've got to restore aromaticity, right? What's going to be the best base available to restore aromaticity? Water. So this water byproduct is floating around in solution. This water will grab this proton, clamp down, and restore aromaticity to the entire system. So if you want, with nitro groups, you can show each individual bond, like the Zwitter ion. If you want to just abbreviate it, NO2, I'm fine with that as well. However, you should know what NO2 means as a Lewis structure, right? So pretty interesting chemistry. Like I said, this was really popular in the early 1900s for making explosives. In fact, it's still used today for making a lot of explosives. If you're interested in a fascinating book, there's a book called The Alchemy of Air. Basically, the reactions for creating nitric acid were hugely important, and a lot of people think were responsible for triggering the outbreak of World War I and II. So interesting chemistry historically. Yep.
I still don't understand the first step of why that oxygen is attacked more so than one performance.
Yeah, so your question is, why not do that?
Yeah.
So if we were to protonate that other oxygen, we don't have any leaving groups. We have nothing to kick off. The reality is, in equilibrium, absolutely, some of that would get protonated. It just wouldn't lead to formation of the nitrosonium ion.
Yeah, so how would we favor that?
It's not a matter of favoring it. It's just a matter of it kind of being instead of going down the highway, you're ending up in a cul-de-sac. You can still drive up and down the cul-de-sac all day long, but you're not going anywhere useful. So we're trying to ultimately get to the nitrosonium ion because that's the useful direction that will lead to reactivity. Does that make sense?
Yeah, it's just, I understand it's more useful, I just don't see why that happens with the other.
Yeah, the reality is under equilibrium conditions, we're going to have a whole variety of different species present. This is just the reaction pathway that will lead to reactivity. Yeah, exactly. Good question. All right. So there's another cool trick you can do with this. Yeah.
So does it end with the charges still on there, or?
Yeah. So the question was, does it end here with the charges on it, right? Yeah, the reality is because it's a Zwitter ion, it's stable as a Zwitter ion. That negative charge will delocalize across both oxygens, and so it's relatively stable. Yeah. So I'll show you a cool trick with this. All right, and this cool trick involves using the product that we just made. What would the name of our product be? Nitrobenzene. Okay, so we're starting out with nitrobenzene. And if you treat this with hydrochloric acid and iron or zinc, you can actually reduce that nitro group. This will also work with catalytic hydrogenation. And when that happens, the reduced product is now an NH2 group. What would this be called? Aniline. So we can actually interconvert nitro groups pretty readily. We'll talk more about why that's useful later. But let's think about this. Is a nitro group, meaning what we just formed here, is that going to be electron withdrawing or electron donating? Let's think about it. We do have electrons here. If I push these electrons in, do they end up going into the ring? No, they just end up getting shuttled to the outside. So really, we don't have resonance structures where we can push electron density into the ring. However, we do have a resonance structure where we can pull it out, right? So nitro groups are good electron withdrawing groups due to resonance. We can pull electron density out of the aromatic ring. Now let's think about aniline. Is aniline an electron withdrawing group like a nitro group, or is it electron donating? It's donating. Really, the only option it has as a substituent is to donate electron density into the ring. We can't pull it out in any meaningful way. So it's a useful way of turning what was an electron withdrawing group into an electron donating group, and that changes the reactivity of a lot of these molecules. All right. The next one is pretty powerful and unique. This one's called Friedel-Crafts Alkylation. It's kind of a mouthful. All right, and with Friedel-Crafts Alkylation, again, we're going to start out with an aromatic molecule. And I'm going to abbreviate our group as RCl. What do you think that R stands for? Any sort of alkane, right? So it's just your standard alkane. So it could be an ethyl group, it could be a methyl group, it could be a tert-butyl group. It doesn't really matter. It's just an alkane of some sort. And then we're going to also use a catalyst, which in this case is aluminum trichloride. And when all is said and done, you can install that alkyl group directly on the aromatic ring. All right, it is important to remember that an alkyl group by its very nature is an alkane. It's not something else. So it's got to be some sort of alkane type system coming off there. So let's take a look at the mechanism and figure out what's going on. And luckily, it's fairly intuitive. I'm going to pick this starting material. What would this be called? Everyone's just mumbling to themselves. All right. You could call it 2-chloro-2-methyl-propane, but most people would call it what? Tert-butyl chloride, right? So we could call it either way, but it is important to remember IUPAC names. All right, and then we've got aluminum trichloride floating around. And like we said before, aluminum trichloride is a good Lewis acid where it's got this empty p orbital hanging out. What do you think the next step will be? Yeah, the chlorine's going to donate its electron density to that p orbital. Oops. We're going to have a negative charge here and a chlorine with a positive charge. All right, this is really, really unstable as an intermediate. Like we said yesterday, halogens don't like having a positive charge and they don't like having two bonds associated with them. So instead, what will happen is this will actually fall apart and dump electrons to that chlorine. All right, so in this step, we've made a tertiary carbocation, right? What's a really important thing to remember anytime we form a carbocation? Rearrangements. Will this rearrange? No, it's already in its most stable cationic form, so we don't need to worry about that. But I did want to make a note here, and that is to always watch out for rearrangements. This happens a lot with these reactions, and oftentimes we purposely try to use starting materials that avoid rearrangements because we know it will rearrange if it can. All right, in the next step, now that we've got a really good electrophile made that's incredibly unstable, we can have our aromatic ring attack it. So in this step, one of these pi bonds can now attack that carbocation. And we end up with this sigma complex or our uranium ion. And just like before, we've got this aluminum byproduct still floating around. We've got 4 chlorines coming off of it. In our last step, this chlorine, along with its electrons, can grab this proton, clamp down, and we can restore aromaticity to the entire system. So really the entire chlorine right here with its electrons is acting as the base, right? It's a little bit weird to think about it, but these chlorines are loosely coordinated to the aluminum. This is also a Lewis acid-base adduct, so really it's kind of like chloride acting as the base. We normally don't think of chloride acting as a good base. Why is that? Because it's the conjugate base of a strong acid, right? But in this case, why do you think it's overcoming that? Why is it acting as a base here? Yeah, exactly. The intermediate is so unstable and forming aromaticity is so beneficial that really this proton is wickedly acidic. So it has no problem deprotonating that position, even though it's a really, really, really weak base. All right, so now we've restored aromaticity to the system and we've made tert-butylbenzene. We've reformed our aluminum trichloride catalyst and we've generated HCl as our byproduct, right? So it's a little bit similar to the halogenation reactions that we saw previously. Yep.
So if we have excess reagent, can we do that more than once?
Yes, so then the question is, if we have excess reagent, can it happen more than once? Absolutely. In fact, that's one major pitfall with this reaction is it's hard to control. Oftentimes it'll run away from you and over-alkylate. Yep.
Would this work with like a brominated alkane instead of a chlorinated one, or no?
Yeah, it will work with any sort of halogenated alkane with the exception of fluorinated alkanes. Fluorine carbon bonds are surprisingly strong and they don't really work in this situation.
Would you need to change the aluminum to whatever the matching thing is, or would you stick with aluminum trichloride?
That's a good question. The catalyst for this can vary a fair amount. In fact, some reactions you don't even need a catalyst. So this is one they kind of gloss over in the book. They don't show it. But let's say we've got benzene right here. And then we've got sulfuric acid. This will accomplish the same reactivity. And why do you think that is? What do you think's occurring in this reaction that's different than what I just showed you? Yeah, so the first step is we would protonate this alcohol, then water would fall off. We'd get the same intermediate. It can still do that same reactivity. So really, there's a variety of catalysts we can use. In this one, they use acid. It just depends on the situation. If you use bromine, oftentimes iron tribromide's used. Even with that, a lot of times you're choosing a catalyst depending on the solubility and the system. And quite often, you're just looking at what's worked well in the past. All right. So let's take a look at this one. We'll say determine the products. All right. So in this one, we're going to start out with benzene. We're going to treat this with 1-chloropropane and aluminum trichloride. And for the next one, we're going to do a really similar reaction. Using ethyl chloride and aluminum trichloride. You don't need to do the full mechanism, but let's try to predict the product or products. So I'll give you a minute to think about it and then check with your neighbor. For the first one, how many products do you think we could get out? 2. All right, so let's take a look at the potential products for the first one. One product is pretty intuitive, right? We could just add in the propyl group directly, right? So that's one possible product. What else could happen? The isopropyl cation could rearrange, right? In which case we might get a propyl group, but instead of it being a normal propyl group, it'll actually be an isopropyl group. Which one do you think we'll get more of? Isopropyl group. And that's actually seen experimentally. When you do this reaction, you get about 65% isopropyl benzene, and you get about 35% of propyl benzene. So again, this is confirming the fact that if something can rearrange, it will rearrange, and usually it'll favor the rearrangement over not rearranging. All right, what about the second one? How many products will we get? 1. But it's a primary group. Why doesn't it rearrange? It'll give you the exact same cation, right? Trick question. So this is something that's important to realize. We have to be super duper careful with the reagents we pick. If we choose a reagent where we form a carbocation that can rearrange, it's very likely that it will. However, if we choose a primary carbocation that, if it rearranges, gives you the exact same carbocation, it doesn't really make a difference. So we can do this bottom one as well. Does that make sense? It's one of the most common mistakes students make is they immediately jump to this one and they completely forget about this one over here. Yeah?
Is there a way to prefer the alchemy product?
So the question is there a way we can favor this? Yes. But we have to do more steps. It's not a one-step process. But we'll get to that in a minute here. All right, so this reaction is pretty neat. However, there's a huge number of limitations. So I wanted to kind of rattle them off. So the first one that we just went over is that we have to worry about rearrangements. So primary alkyl halides can rearrange. with two important exceptions, and that is not ethyl groups or methyl groups. Because we know that if an ethyl group or an ethyl carbocation rearranges, it's the same carbocation. A methyl carbocation doesn't even have the ability to rearrange, so we don't have to worry about it there. All right, number two is that it only works with alkyl halides, not any other ones. And what I mean by that is if you have an sp2 hybridized alkyl halide, it won't work at all. So let's say we're trying to do the following reaction. This would not work because this carbon where the chlorine's attached is sp2. There are other ways to accomplish this transformation, but we can't use this sort of chemistry. Yeah?
If it was a longer chain, would it still mess with it or no?
In general, really simple alkanes are used because we're making an electrophile that's so unstable, it's really not compatible with most other functional groups. Does that make sense? All right. Number three is related to a topic we're going to discuss a little bit later. But alkyl groups are activating. We'll describe what activating is in more detail, but that basically means once you add one, it really, really wants to add a second, and then so on and so on. So it'll run away from itself. So let's take a look at what I mean by this. So let's say we start out with benzene, and we use tert-butyl chloride and aluminum trichloride. We could easily add in that tert-butyl group. And if we think about benzene, we said that benzene's a weak nucleophile, so I'll just say that this is less nucleophilic. However, once you add that tert-butyl group on, it actually becomes slightly more nucleophilic. So as soon as you make some of this in solution, it'll find any remaining tert-butyl chloride and aluminum trichloride and continue to react. So really it's a competition, right? The best nucleophile that's present in solution will be the first thing to react. And so it'll react, and then you'll get two different tert-butyl groups added on. So oftentimes these are really, really hard to control due to their activating nature. Does that make sense? Yeah. Yeah, so the question was about the second one. We'll talk about which positions those additional ones will be put in. Usually, they'll be favored in the ortho positions. And what I mean by that is the ortho positions right there and right there, or in the para position. Why do you think the ortho position might not be favored in this situation? Sterics, right? You'd have two really big groups next to one another, so para tends to be a bit more favored here. Yep.
So if you do the reaction with just one equivalent, you're still going to have a mixture of different.
Yes. So the question was, even if you control your stoichiometry and add things in the appropriate ratio, because as soon as you make, let's say, one molecule of this, it's all of a sudden your best nucleophile in solution. It's going to find any remaining electrophile and outcompete it. Yep. All right. The next pitfall. Yep.
So that one's going to be the maker.
It's hard to control. I wouldn't necessarily say this product over here would be our major product. I would say we likely would get a mixture, the ratio of which I'm not entirely certain. Yeah. All right. The next one has to do with strongly deactivated aromatic rings. Oh, I can count. So strongly deactivated aromatic rings can't do this reaction. And what I mean by that is, let's say we start out with nitrobenzene. We know how to make that now. We previously said that this nitro group is really, really electron withdrawing due to resonance, right? We can pull electron density out of the ring. And if we try to do this reaction, meaning the Friedel-Crafts reaction, typically no reaction will occur, or if you get reactivity, it's really, really slow and sluggish. And that has to do with the fact that this benzene is actually less nucleophilic because it doesn't have very much electron density anymore, right? This is true exclusively, I would say, for really strong electron withdrawing groups. If you have an electron withdrawing group that's only weakly electron withdrawing, then you can still accomplish these transformations. They just tend to be slower. Yep.
So for electron donating, it would still progress.
Yeah, if it's electron donating, you actually run into this problem, right? If it's electron donating, you actually have too good of a nucleophile and it can actually run away from you. Yeah. All right, there's one other reaction that's really similar to all of these, so I'll briefly introduce it and then we'll finish it up. I think we might have time today even. And this is the Friedel-Crafts Isolation. It's really similar. We still start with an aromatic ring, but instead of using an alkyl halide, we use what's called an acid halide. Right, so this is a really reactive species right here because chlorine, we know, can act as a pretty good leaving group. And when we do this reaction, we can get an acyl group attached directly to an aromatic ring. So this is called an acyl group. So it's similar, but a little bit different. Let's take a look at the mechanism for this one. All right, the mechanism essentially starts in the same way as our previous one, where we've got this chlorine coming off of our acid halide. We've got aluminum trichloride floating around, which we know from all of our other reactions is a good Lewis acid. So the question is, what will happen in this next step? Yeah, the chlorine can attack in. Why not the oxygen? Well, let's think about it this way. Which one's more electronegative? Which one wants to hold on to its lone pairs more tightly? Oxygen, right? So chlorine's less electronegative. It's got electrons that aren't being held as tightly. That means they're better at being donated, right? So we can go ahead and form this Lewis acid-base adduct. Again, we've got this super duper unstable chlorine with a positive charge. So in this next step, something unusual happens. Just like before, we're going to dump off that chlorine. We're going to form this carbocation, right? So I'm going to actually show the carbon here just so we can keep track of things. So I'm labeling that now with the C. And this looks really, really, really unstable, but there's something else stabilizing it. resonance, right? So you can show a resonance structure where you dump in one of these lone pair electrons. And because of this, this is relatively stable for a carbocation. Which one's our major contributor? The right or the left? Everyone's giving different answers. All right, what's the most important thing we look at when we're looking at major contributors? Octets being full. Which one has full octets? The one on the right. So this one is actually our major contributor. So really that carbon-oxygen bond is more like a triple bond at this point than a true double bond. So this is called the acylium ion. So just like an acyl group, it's an acylium ion because it has a positive charge on it, right? All right, and then in the next step, we've got this aromatic ring. Any sort of aromatic ring could be substituted. And then one of these pi bonds is going to attack this carbon. People will ask me, does it matter which resonance structure we use? No, doesn't matter at all. You can use either one. And we'll get that sigma complex. Make sense? And then just like before, we'll have aluminum floating around. Whoops. With its fluorochlorines. We know that one of these chlorines is pretty loosely coordinated, so it can act as our weak base, steal that proton back, and restore aromaticity to the system. Oops, I forgot my negative charge here. We regenerate our catalyst, and then we also generate HCl. So getting back to John's question earlier, will this work if you have an acid chloride where you've got a bromine on there? Yes. However, those reagents are so wickedly unstable, they're quite uncommon. Usually when you're working with acid halides, you're working with chlorines, not bromines.
You want us to draw the resonance structure as well?
So in general, unless I specifically say draw all the resonance structures, I'm fine with you not showing them. That's a good question. All right, so we saw with the Friedel-Crafts alkylation, we ran into the problem of over-alkylation. Do you think we're going to run into that here?
No.
Why not? Yeah, if we think about resonance here, the only option for this one is pulling electron density out of the ring. That means that this is an electron withdrawing group. That means that the electron withdrawing group makes this less nucleophilic. And prevents over-acylation. All right, do we have to worry about rearrangement? Will this sort of carbocation rearrange? No, it's already resonance stabilized. Resonance is way better than anything else, so why lose that resonance? So in this case, we don't need to worry about over-alkylation. We don't need to worry about over-acylation. In many ways, this is a pretty rugged reaction. Does that make sense? Yeah.
If you want another acylation to happen, is there a way to drive that forward?
You can push these reactions to go. Typically, your next reaction will be a lot slower because your product's less nucleophilic than benzene, right? So we'll actually talk about that later on this week. We'll talk about activated aromatic molecules versus deactivated. Activated means that the aromatic ring has an abundance of electron density, meaning the next reaction will be very fast. If it's deactivated, that means it normally has an electron withdrawing group. It's going to be less nucleophilic, and the next reaction will be slower.
Okay.
Yeah.
So it can still have it, it just
Yeah, it can still happen. It's just the reaction rate will be much slower. Yep, good questions. All right, I think that's where we'll stop today. Tomorrow we'll continue on, talk about some new reactions.